Hello everyone. In October of 2017, an unusual object appeared in one of the sky frames scanned by the Pan-STARRS telescope system. This moving celestial object appeared to be an ordinary asteroid. Its brightness was low, and the path it followed was quite unclear. But it was quickly noticed that its orbit didn't resemble anything typical, not that of a planet, a comet, or even an asteroid. The path it traced was hyperbolic, meaning it wasn't bound to the sun and was moving away never to return. For the first time, an object clearly arriving from beyond the solar system had been observed. Calculations revealed that this object, later named Oumuamua, was traveling at about 16 miles per second before approaching the sun, and continued on its way at that same speed. That meant it wasn't just fast, it also hadn't been slowed by the sun's gravity and hadn't entered into orbit. In other words, this object carried enough energy to break free from the sun's gravitational pull entirely. Initial telescope observations revealed that it was rotating, but irregularities in its spin suggested either a non-uniform surface or an unusual structural shape. On top of that, the way it reflected light drew attention. Its brightness didn't remain steady like a solid surface, as if it was changing with irregular brightness from different angles. So what exactly was this object, and where did it come from? When its trajectory was traced backward, it appeared to have come from the direction of the Lyra constellation in the Milky Way. But that alone wasn't enough to pinpoint which star system it might have originated from. In the vastness of interstellar space, it could have changed direction, lost speed, or collided with other objects over millions of years. All we had was an entry point, the rest was unknown. So the real question became, why was this visitor so unusual? The mystery that began with Oumuamua's detection only deepened as scientists analyzed its behavior. This object didn't fully match any known category of celestial body. It looked like an asteroid, but accelerated like a comet, altering its path while showing no signs of gas release. Observations revealed that Oumuamua experienced a small but measurable acceleration as it neared the sun. This is something typically seen in comets. When solar radiation causes frozen gases on the surface to sublimate, the outgassing creates a thrust in the opposite direction. But Oumuamua showed no such mechanism. There was no visible gas trail, no dust cloud, and no trace in the light curve to suggest vapor or particle emissions of any kind. Its rotation was also highly unusual. Most known celestial objects rotate steadily around a single axis, but Oumuamua exhibited a kind of tumbling or unstable spin. This raised more questions about its internal structure and external geometry. Perhaps it wasn't symmetrical, or maybe its surface had regions of varying density. Both could potentially explain the motion. Still, the data wasn't sufficient to confirm either scenario. Models based on the object's light curve produced conflicting conclusions about its shape. Some suggested that Oumuamua was extremely long and narrow, almost cigar-shaped. Others favored a thin, flat, disc-like form. In either case, the shape was extraordinary. Such proportions had never been observed in any asteroid or comet before. Another curious aspect was the way its surface reflected sunlight. The object reflected light quite strongly, but not in a consistent pattern. This led to speculation that the surface might be metallic, icy, or unusually smooth. Yet no definitive data could confirm its chemical composition or surface morphology. So what could be behind all these undefined behaviors? The question of what Oumuamua actually was remained unanswered after the initial physical analyses, but the real debate centered on its acceleration. This motion, which couldn't be explained by known laws of physics, raised the question, had it occurred through natural mechanisms, or was something else at play? Astrophysicist Avi Loeb from Harvard University offered a different explanation. According to Loeb, Oumuamua's acceleration could only be explained by a surface driven by photon pressure. In other words, sunlight might have struck an ultra-thin structure, giving it a gentle but continuous push. This mechanism is known in theory and has already been tested in small-scale space missions launched from Earth. Known as a light sail, this technology enables propulsion in space without using fuel. This suggestion brought forth the idea that the object might not be a natural formation, but a deliberately engineered structure. If Oumuamua was a light sail, it would have to be made of a wide, thin, and extremely lightweight material. According to calculations, such a structure would need to be thinner than a human hair, yet tens of meters across. For something so delicate to survive an interstellar journey, it would likely require artificial engineering. So how seriously was this idea taken? The scientific community had mixed reactions. Some researchers argued that Loeb's hypothesis needlessly attributed artificiality to a phenomenon that could eventually be explained by natural processes not yet fully understood. Others said that while the idea was speculative, it shouldn't be dismissed. The data was insufficient, but the observed behavior was anything but ordinary. At the heart of the debate were these questions. If it was a light sail, who did it belong to? If it was deliberately sent, what was its target? And more importantly, why was it so silent? Loeb proposed that such structures could be cosmic postcards carrying messages across galaxies. Perhaps it was a piece of technology sent by another civilization hundreds of thousands of years ago, now inactive, like an empty bottle washing ashore on a distant beach. Avi Loeb's idea also opened the door to a much bigger question. If Oumuamua were a spacecraft, how would we even recognize it? One of the methods typically used to detect an artificial object is to look for signs of attitude control. Spacecraft usually regulate their spin, try to maintain orientation, or emit signals. But no such behavior was observed in Oumuamua. Its rotation was unstable, as if no control system existed or it had stopped functioning. Some speculated this might indicate a failed probe. Another possibility is that Oumuamua was a passive structure. In other words, a platform carrying no control system, engine, or power source, simply drifting through interstellar space. If so, the object might be nothing more than a piece of space debris, no longer performing any task. Such a structure would emit no signal, change no direction, and remain only as the remnant of a long-lost technological purpose. If this object really was an artificial structure, the most concrete clues would have to be found in its shape. Surface properties, reflection patterns, and geometric proportions could all point toward a design built with engineering intent. Although Oumuamua's shape couldn't be determined with certainty, modeling efforts yielded two extreme possibilities. It was either long and narrow or flat and disc-like. Such extreme forms are rarely seen in nature. Still, no clear evidence of directional alignment, symmetry, or geometric regularity was obtained. Perhaps the structure had eroded over time or lost its original shape due to collisions. The spacecraft hypothesis must also be considered not just in physical terms, but temporal ones. Oumuamua could have drifted through space for millions of years. Over that time, any onboard power systems might have shut down, its surface might have been coated in cosmic dust, or all of its functionality could have ceased. If it was once a piece of advanced technology, it might now be nothing more than a silent, inactive object. Public reactions to this idea were also noteworthy. On forums and science platforms, some speculated that Oumuamua might be a form of cosmic wreckage or a derelict exploration probe. Some users described it as a failed control system. Others suggested it resembled a drifting navigation platform. As the debate over whether the object was artificial continued, attention turned back to the sky. Were interstellar objects like this truly common, or was Oumuamua just a rare exception? That question was answered 2 years later. In 2019, an amateur astronomer from Ukraine, Gennady Borisov, discovered a new object. Its trajectory was clearly hyperbolic, meaning it too had entered the solar system from the outside. But unlike Oumuamua, this object behaved in very familiar ways. Named 2I Borisov, the object looked and acted just like a comet. As it approached the sun, surface ices began to vaporize, releasing gas and dust from its outer shell. A visible tail formed, one that could be tracked in detail. This outgassing also caused small deviations in its path, just like long-period comets within our own solar system. The gases released by Borisov were also chemically analyzed. Spectral data revealed the presence of compounds like carbon monoxide, hydrogen cyanide, and water vapor, molecules commonly found in comets that originated closer to home. These similarities suggest that, even if Borisov came from an entirely different star system, it likely formed under chemical conditions similar to ours. No unexplained acceleration or unusual reflection patterns were seen with Borisov. It wasn't mysterious, just foreign, and that made Oumuamua stand out even more. Both objects had entered our system on high-speed hyperbolic paths, but only one displayed physical anomalies. So, what would a third example tell us? On July 1, 2025, the Atlas Telescope network in Chile recorded an image of a faint dot slowly moving across the sky. Initially cataloged as an ordinary comet, the object soon began to follow an unusual trajectory. Calculations showed that it wouldn't orbit the sun. Instead, it was simply passing through the solar system and continuing outward. In other words, the object had an interstellar origin. The International Astronomical Union designated it as Atlas, the third confirmed interstellar object. Its inbound velocity was measured at about 40 miles per second. That's well above the minimum escape velocity needed to break free from the sun's gravity. Based on brightness data, the object's diameter is estimated to be around 12 miles, making it significantly larger than both Oumuamua and Borisov. Observations show that Atlas behaves like a faint but fairly typical comet. As it approached the sun, surface volatiles began to sublimate, creating a thin cloud of gas and dust. Some telescopes even recorded a short tail. This activity closely resembles the behavior previously seen in Borisov, the earlier interstellar visitor. While surface data is still limited, the reflected light intensity and spectral analysis suggest that 3I Atlas shares chemical similarities with comets from our own solar system. The fact that 3I Atlas was detected so early in its approach turned it into a unique research opportunity. Oumuamua was already on its way out by the time it was spotted, and Borisov had already become active. But Atlas was caught while it was still within the system, before its behavior had fully developed. This makes it possible to observe both its approach and departure in real time. In the coming days, we'll likely have much more data on Atlas. Still, no irregular acceleration, light sail-like structure, or physical anomalies have been detected in this object either. Everything appears to be as expected. So far, we've observed 3 interstellar objects. The first showed behavior that didn't fit into any known category. The other 2 followed familiar patterns. Why was Oumuamua different? There are 2 main explanations for this. The first is that Oumuamua truly was an exceptional object, structurally, chemically, or in terms of origin. It may have formed in a very different kind of star system, using materials we're not used to seeing. It could have been a rare, unfamiliar type of body. The second possibility is that the difference comes down to how and when it was observed. Oumuamua was detected too late. It had already passed closest to the sun and was continuing on its way without slowing down. As a result, the time it remained visible was extremely short. Telescopes were only able to collect usable data for about 11 days. After that, the object faded rapidly and moved beyond the range of observation. The limited data window wasn't enough to precisely determine many of its physical parameters. It's possible that Oumuamua had a tail too, but any activity may have ended before it was observed. Or maybe its acceleration came from the release of volatile gases at a level too faint to detect. In that case, the strangeness wouldn't come from the object itself, but from the gaps in our observation. Today, Oumuamua is more than 10 astronomical units away from the sun. Its brightness is far below the threshold detectable from Earth. So even if it still technically exists, it's no longer possible to observe it directly. No telescope aimed at its coordinates can clearly image an object that distant and that small again. Looking back through older observations doesn't help either. Pre-discovery records consist mostly of low-resolution, wide-field scans. In fact, researchers did try to trace Oumuamua's earlier path, but due to its faint brightness, most of these attempts failed. Detecting a dim, stationary, point-like object against the star-filled background was nearly impossible. Reaching the object with current technology isn't an option either. Oumuamua is leaving the solar system at around 122,000 miles per hour. No spacecraft we have today could catch up with it. On top of that, it shows no signs of maintaining a fixed direction or carrying any kind of communication system. It's not just out of sight, it's out of reach. But one thing is clear. Among all the interstellar objects identified so far, Oumuamua remains the only one to hold so many unanswered questions.